Hello all, have a nice time. This is the first problem solving session on complex analysis, and today we will deal with Cauchy-Riemann equations and analytic functions. Before going to the problem session, we will state a theorem. Let f of z equal to u of xy plus I v of xy be defined and continuous in some neighborhood of a point z equal to x plus iy and differentiable at z itself. Then at that point, first order partial derivatives of u and v exist and they satisfy the Cauchy-Riemann equations. What are the Cauchy-Riemann equations? That is ux equal to vy and uy equal to minus vx. It's a equation connecting the partial derivatives of u and v with respect to x and y. So the equations are ux equal to partial derivative of u with respect to x equal to derivative of v with respect to y. Ux equal to vy and uy equal to minus vx. If f of z is analytic in a domain D, those partial derivatives exist and satisfy the Cauchy-Riemann equations at all points in the domain. And in the converse part, we have if two real valued functions, continuous functions actually, u of xy and v of xy of two real variables x and y have continuous first partial derivatives that satisfy the Cauchy-Riemann equations in some domain D, then the complex function f of z equal to u of xy plus I v of xy is analytic in D. That is, if you have two continuous functions u of xy and v of xy which satisfy the Cauchy-Riemann equations, then the corresponding complex function f of z equal to u of xy plus I v of xy is analytic in the domain. So using these concepts, we will do some problems today. First type of problems is you have to check whether given functions are analytic or not. So we will use the result that if a function is analytic, then if we write the complex function f of z as u plus iv, this ux equal to vy and uy equal to minus vx. So this is the Cauchy-Riemann equations. So if you want to check whether a given function is analytic, you just check these equations. Whether ux equal to vy and uy equal to minus vx. So we will do one or two problems. So first problem is f of z is equal to I into z bar. So you want to check whether this function is analytic or not. For that, you have to express the function in the form u plus iv. So actually, we will write I into z bar is mod z square. So I may write mod z square. That is I into mod z square. Z is equal to x plus iy. Then mod z is equal to square root of x square plus y square. So mod z square is x square plus y square. So I may write I into x square plus y square. So this is a function f of z. So the real part of this function is equal to 0. Okay. So u is equal to 0 and v equal to the imaginary part of the function, that is x square plus y square. So what happens when you find ux equal to 0 because u equal to 0. And what about vy? So this is equal to the partial derivative of v with respect to y. So it is 2y. We may consider x as a constant here while we find the partial derivative with respect to y. So vy equal to 2y. So we may conclude that here ux is not equal to vy. Ux not equal to vy. Therefore, this function is not analytic. Another problem, f of z equal to e raised to minus 2x into cos 2y. Another problem, f of z equal to e raised to minus 2x into cos 2y minus I sin 2y. Here we have to express f of z in the form u of xy plus I into v of xy. So we will multiply e raised to 2x here and we'll remove the bracket and you can write the function in this way. So u is equal to real part e raised to minus 2x into cos 2y. V is the imaginary part of f of z, that is minus 2 e raised to minus 2x sin 2y. So you can find ux and uy. While finding ux, we are considering this y, cos 2y, as a constant function. So this is equal to derivative of ux is equal to derivative of minus 2x with respect to x. That is minus 2 into e raised to minus 2x. This cos 2y is treated as a constant, so we multiply with a constant. Okay. Now finding uy, we may treat this e raised to minus 2x as a constant. So e raised to minus 2x into derivative of cos 2y is minus 2 sin 2y. Similarly, v is equal to minus e raised to minus 2x sin 2y. Let's find Vx and Vy, and you can see that Ux and Vy are equal. Ux is equal to Vy and Uy equal to minus Vx. Therefore, here U and V satisfy the Cauchy-Riemann equations. Therefore, the corresponding function is analytic. Now we may do the fifth problem. F of z equal to real part of z square minus I into imaginary part of z square. So here the function is not written in the form u plus iv. So we substitute z equal to x plus iy. Then what happens? Z square is equal to x square plus 2x iy plus iy's whole square, and combine the real part. Here I square is minus 1. So you have x square minus y square plus I into 2xy. Okay. Now the z square is x square minus y square plus I into 2xy. Here in the question you have f of z is real part of z square. So that is x square minus y square. Okay. Minus I into imaginary part of z square is 2xy. So we substitute here 2xy. Now you can find u and v. What is a u? U is a real part of f of z, that is x square minus y square, and v is the imaginary part of f of z, that is minus 2xy, because you have to consider f of z as u plus iv. Okay, so v is minus 2xy. Now when you find ux, uy, vx, vy, we will get like this. Ux is 2x and uy is minus 2y. Here when you find uy, x may be treated as a constant. Therefore, derivative of x square becomes 0. Similarly, vx equal to minus 2y and vy equal to minus 2x. So when you compare ux and vy, we may see that these two are not equal. Ux is not equal to vy. Therefore, the function doesn't satisfy. So here u and v doesn't satisfy Cauchy-Riemann equations. Therefore, the given function is not analytic.